Okay, welcome to my talk on Scimitar, Functional Programs as Optimization Problems. I'm Nate Bragg, and this is a collaborative work with my advisor, Jeffrey Foster at Tufts, and my collaborator, Philip Zucker at the Charles Draper Laboratory. So, okay, this work is motivated by the recognition that algorithms often need optimal values, but that we settle for acceptable values. And this is in domains like logistics, optimal control, resource allocation, and computer-aided design. Oftentimes we turn to approaches like ad hoc algorithms or greedy algorithms or high watermark algorithms, but these can be suboptimal, and it can be very hard to specify certain constraints in those systems. And it's very common for the business logic and the constraints to be mixed, which makes the overall implementation less maintainable over time as you make changes. And so a better approach is to rely on optimization solvers. And our work Scimitar combines optimization with a functional programming language. And to give you a taste of what that's like, let's look at an example of a traditional summing function. So on the left side here, we see some code. This is the normal implementation of a sum to n function that you get an increasing accumulator and a monotonically decreasing number n. And normally here we have a fixed n, and we add up to that n. But here instead we have at the bottom, you can see we have a constraint that says in fact the result has to be greater than or equal to 100. We actually want to know n. And so we want, at the very first line we want to minimize n. We want the minimal n such that that constraint holds. And so in this case, it would appear that it recursively runs backwards to get the result for n of 14, which if you verify it is indeed correct because it adds up to 105, which is greater than or equal to 100. All right, so we need a little bit of background to understand this. The first is how to find optimal values. So this has been thoroughly studied and has spawned the field of mathematical optimization. The mathematical optimization asks the question, what is the best value for a cost function? And so the cost function, so named because it's very common for us to want to minimize the cost of something, like in a logistics context. These problems often include constraints, and with the goal that we want to rule out certain values. And the common formal presentation is to maximize or minimize some function f subject to some variables x, subject to some constraints g sub I for all I, whatever we care about the number of constraints that we have. And so you can get kind of an idea with this in the figure that we're trying to find this minimal point over here. All right, so it's very common one very common method of optimization is linear programming, also known as LP, which has a linear cost function and linear constraints and real variables. And there's an extension, mixed integer linear programming, that combines linear programming with integer variables. MILP is very useful because it applies to many different problems, and there are many efficient off-the-shelf solvers. For example, Gurobi, Cplex, Coinor, CBC, and many more. And so this is great, but when we have more complex problems, suddenly we can't just give it a constraint system that becomes too complex to maintain. We have to rely on expert encodings of more advanced kind of features. So the expert encodings are very expressive. You can do all kinds of things with them that you can't do with the bare bones constraint system, right? But as you grow them, they're complex enough that it becomes unmaintainable. And some examples of expert encodings include Booleans, multiplication, and conditional, like solve time conditional branching. So to give you a vague idea here, don't bother trying to understand this. It's gibberish. It's meant to just show some ideas like we have if-then else's, we have assert embedded in here, some constraints, right? Comparison, multiplication, vector referencing, Boolean algebra, lambdas and recursion, right? And so when we lower this program into a system of constraints, it's very complicated. And if we change one thing in that, it changes everything, right? Because they're all interrelated. So for example, if you want to tweak that lower assert there in the middle of the if-then else, you want to pull that out to a different part of the program, suddenly everything else in the program needs to change, all the variables, the vector referencing, the Boolean algebra, maybe, maybe not, but the inlining of the lambda has to change, etc., right? But ostensibly, we can change that code very easily. The MILP constraints not so easily, and that's because the expansion here is, like I said, is complex. So multiplication expands to equivalent to the logarithm of the c and the logarithm of the x size of those variables. Up here, if you see the multiplication on the first line, c times x, right? Vector reference expands to the number of constraints and variables up to the length of the vector, which could be enormous, right? Lambda is inlined up to some user-defined limit, which could be quite large, and whatever you put in the lambda, of course, gets expanded that many times, right? And if-then else, of course, is the most complex because it expands its asserts, its interior asserts, into an overall path condition for each individual assert. So if you, like I said a minute ago, if you take that inner assert and you move it, suddenly a lot of the asserts have to change, especially if you swap the true and false branches of something. You could have a ton of asserts that suddenly have to change. And the size of that path condition is proportional to the depth of the assert. And so if you have a highly branching program, suddenly this, like I said, it becomes completely unmaintainable. And so the MILP program is ostensibly write-only. And the second piece of background knowledge here is called solver-aided languages. This has been studied for a while. Existing languages include SWI Prolog, Daphne, and Rosette. They focus on SMT or similar decision procedures. Target applications are therefore quite different than mathematical optimization, but they usually rely on efficient off-the-shelf solvers also. The problem is they yield only satisfying results, not optimal ones. And so in our work, we introduce Scimitar, that is an approach that embeds an optimization solver into a functional programming language. We combine these to embed this MILP solver in our scheme-like language. Scimitar is a compiler from the high-level language into this constraint system. We wrote it in Racket. The solver we rely on is Gurobi. And all of these expert encodings we were talking about a moment ago, they're all performed automatically, so you don't need to worry about that. And therefore, because of that, the semantic coupling is reduced because you no longer have to worry about this whole program organization, right? And it yields optimal results, not just satisfying. Okay, so for an example of why you might want to use something like Scimitar, consider an allocator like malloc, right? So we have our code here on the right, defines an allocate function we'll talk about in a second. So in systems with manual memory allocation, the runtime needs a way to track the free memory so that you can give off an allocation when it's requested. And a common approach on limited platforms like embedded systems is to use a bucket-based arena. If you take a look at this little chart here, it shows it's broken down into buckets of different sizes, large, half, a third, etc., right? And so the idea is if you ask for something small, you'll get it out of the small bucket. If you ask for something large, you'll get it out of the large bucket. And the code to do something like this, you ask for something of a certain size, you're given the bucket. In the end, you're given a block from that bucket. But in the meantime, we might have to change the allocation of it, because as a program evolves, of course, the life cycle of memory allocation means that the types of objects, the types of memory blocks you are requesting, the size changes. It's very different in the beginning versus in the steady state. And so that trade-off of rebalancing, but many ways, it's possible to solve this problem many ways, but we want the best way to rebalance it, right? The function that does this is this update arena dist here. And now let's take a look at that. So we give an implementation of that here. And this is just a silly example, right? It's not representative of some sort of industrial strength example, which would have to consider many other factors. And so recall the minimized term from the sum to n example here. The compiler takes the body of that minimized term and takes all of the encodings and everything and compiles it into an optimization problem that it then submits to that solver. And then the solution to that is marshaled back out using this optimum ref term. All right. So in our implementation of update arena dist, we want to minimize the overall memory usage and then extract the arena because we want to have the next stage in the arena, right? These are determined according to constraints like this one highlighted here and the others down there. The asserts can be over like frozen parameters that come in and other symbolic variables within the solver itself. And each of these constraints depend on the behavior of the rest of the program. The rest of the minimize, right? Because the symbolic variables, they're all live at the same time, and the solver is trying to figure all of them out at the same time so it can optimize for you. So the constraints here, these asserts, they only apply within a branch if that branch is active. So, right, so we have this assert inside this if, but not only can the guard determine whether this branch is active, but actually the branch itself can declare itself to be active because whatever it is over, that is going to minimize the overall problem. And also we can see at the bottom here that update arena dist calls itself recursively. This will eventually settle into a layout that it then returns. And so this is slower than a heuristic for sure. But the goal here is because we're trying to optimize it, basically you're only going to run this extremely rarely, probably just at the beginning, because once the program reaches any sort of steady state execution, it will no longer need to rebalance, in theory. All right, so I said update arena dist recurses, and to do this, it has to step into the minimize block and back out of the minimize block, and we call this crossing the host solver boundary. So this shifts from the usual semantics that you're all accustomed to into the solver semantics. The host language transitioning to the solver language, the concrete variables within the host language are frozen, right, that you can't compute with them anymore inside of the minimize block. And then when you leave the solver and go back into the host language, the symbolic solver variables are marshaled back out and frozen in the host language, right? So they don't continue to remain symbolic. And we can see in the little diagram here, the way this works is as you're executing the host language, going on and on, you reach a minimize block. This goes into the solver language, which takes the minimize block into the compiler. It produces the lower level matrix format that it then hands to the solver. When the solver is done, it returns the value back into the host language. Anything other than a minimize block, it just continues on in the host language. Right, so let's talk about the key contribution here within this minimize block is automatically encoding program features that are present in most traditional languages, but not in optimization problems, and that really you have to be an expert to be aware of. And so there are a lot of these, and we are going to focus here on variable multiplication, which MILP can't do. MILP is not capable of this because it's a nonlinear operation, and MILP deals over linear constraints, right? So the way we accomplish this, though, is we use a technique called McCormick envelopes. It simulates multiplying two variables by creating what they call a convex relaxation, which is what we see in the little figure here. This uses the upper and lower bounds of each variable, xl, xu, yl, and yu here in the top left set of equations, and it turns that multiplication into those four individual constraints. If we fill that in with specific values, we can plug and chug in the bottom left here, and we get different planes that we can draw to make a bounding box. And so the term convex relaxation refers to this bounding box, this is to say, oh, you might have a specific multiplication in mind, but I'm going to draw a box around all possible multiplications and say that, well, maybe some aren't valid, but the answers are in here. And so the reason this is okay in this case is because in practice, the values that don't work correctly are actually ruled out. So during the course of solver execution. And so for our case here in the bottom left, we chose these four values. X is a binary variable between 0 and 1. Y is between -2 and 2. And so the multiplication here, the axes reflect that with y, and the multiplication on the side here. And each face in the diagram represents one of these four planes, right? And there's an invisible triangle on the top here, which is transparent, so we can see inside. So we can see the two triangles in the back here. And so by inspection, we can see that all the vertices are correct here. If you go on the left, when x is 0, it doesn't matter what y is, right? Because that whole edge, the multiplication is 0, right? So that whole edge is in fact in there. And 4 out of the 6 edges of this tetrahedron are valid constraints. So if only 4 of 6 edges are, what does that mean? So it turns out the faces and the diagonal edges in the interior of this tetrahedron, they're not valid. So how can we use this to multiply if the answers aren't valid, right? So it turns out in practice, because we're using a MILP solver, we can actually set one of these to an integer. And when you do that, these edges that are valid answers, everything else is ruled out. And so, like I said, in practice, this means that we can simulate multiplication. And in fact, this can be extended to general multiplication using bit vectors, but not float. That requires a more powerful solver. And so this is an example of our expert encodings. They're important because it can be very hard to actually find these. You actually do kind of have to be an expert. An example of this is McCormick envelopes are very hard to kind of Google and figure out, right? Because if you don't actually know what they are ahead of time, it's hard to find out what the name is, even to look it up. And when you do look it up, there aren't a lot of resources for it, and they are very confusing. So Scimitar provides these automatically, which is kind of nice because then you can just multiply two terms. You don't have to think about the rest. All right, so to demonstrate Scimitar, we implemented several benchmarks, a couple classic optimization problems, maximum pipe flow problem, like a profit resource scheduling logistics problem, the arena allocation problem we saw earlier, and a nifty one called recitation, which optimally assigns students into different recitations and at the same time chooses which recitations to do and their sizes. And so there are a lot of dimensions here because it's not only filling things out, but also their shape. It's deciding the shape, the size, and the values at the same time. So this is kind of a killer app here. And there are others, including some micro benchmarks that I'm not going to discuss. So to get you an idea of what these look like when you actually get into the solver, right? So you can look at the max flow visualization on the left. We have various, edges here, and the nodes in between. We have a source and a sink, and you want to pump a certain amount of, say, fluid through pipes or something like that, right? And on the right here, we see a representation of the resource allocation problem. You have things of a certain size. You want to put them in a certain place. And as you go from left to right, it actually chooses where they go and puts them in blocks together. OK, so in running our benchmarks, our goal was to simply give evidence that the MILP solver has benefits over the more generic approach offered by SMT solvers. And so we did that by comparing Scimitar to the solver-aided language Rosette, which to a certain extent is a comparison of the solvers underneath, Gurobi versus Z3. We split the time between compile and solve, and the differences in performance is that Scimitar, we wrote the compiler for, and it does all its encoding there, whereas Rosette passes all the work off to Z3 and uses SMT2lib as a backend. And so I want to emphasize here that Z3 is not an optimization solver. The algorithms it uses fit their application domains rather closely. And so our expectations is that by using a dedicated MILP solver, we will be able to outperform them when it comes to actually solving things. And so we'll analyze these on the next slide. But real quick, just to make a note, unfortunately, the compile times for Scimitar are slow, but the solve times are significantly faster in most cases, which gives evidence that we're right, that dedicated MILP solvers can provide benefits. And there are a couple cases actually where Rosette actually didn't even finish. It met a timeout, a 20-minute timeout. OK, and so what do all these mean? So in Scimitar, our compiler does dominate. Because Z3 dominates the time in Rosette, our MILP performance is usually better, with some exceptions. The pipes is slower because sometimes you just get randomness in there and you had a bad start or something like that. But our tests show that the MILP solver scales very well, which supports our claim. The problem sizes, unsurprisingly, correspond to the compile and solve time. And as far as our compiler goes, it's implemented in Racket. Racket is slow. C rewrite would be much faster. So we're going to pass that off to somebody else's fault. So in summary, we present Scimitar, which is an optimization-aided functional programming language that reduces coupling as compared to a MILP solver, gives expert encodings for non-experts. The solver itself outperforms a general SMT approach. And our targets are traditional optimization problems, optimal control problems, resource allocation, generating code, design optimization, et cetera. All right, well, thank you very much.
Thanks very much. We have lots of time for questions. Let me kickstart while you're thinking about that. As a complete outsider, completely ignorant, what are the kinds of problems that you can't do for which you do need an SMT approach? I'm just...
Oh, that's very interesting. Yeah, so anything that a SAT solver can do at its basis relies on making kind of true-false assignments. SMT is an extension of that, right? MILP can also do that. If you make everything an integer variable, then it too can come up with those exact satisfying assignments. But it's going to be much slower. There's no free lunch. And so for those kinds of problems, SMT is going to beat it. But if you're actually minimizing, the algorithms that SMT solvers use are, again, tailored to that domain. And so they will not perform as well when you're actually minimizing or maximizing.
OK, thank you. Questions? Great.
So for the Rosette comparison, did you encode what were the optimization criterion encoded in SMT? Because usually it's minimized something subject to whatever. So how do you, like you have a minimize, you're trying to minimize something. The SAT is just trying to find a solution. So
That's right.
are you encoding different information to the solvers?
No, the programs are almost exactly the same across the two. There are a few little differences, like actually invoking the solver itself.
Right.
But so squirreled away deep within the Rosette API is a minimize function to submit to Z3. Z3 does have a minimization algorithm.
I see.
Yeah, it solves max set by an algorithm called max res, and so which is again not as fast as the MILP algorithm, the common MILP algorithms, right? But they never explored this in any of their work. So as far as we're aware, this is the first look at actually tackling optimization in a solve-rated language.
And just small follow-up. So you compared you had the compile and solve times, but what about the values that were outputted in the end? Like, did they both find optimal?
I see what you're saying. Yeah, they're always the same, except for the case where they're two equally good.
Okay.
And then even Scimitar sometimes will just pick the other one very happily and say, well, today I'll give you the other side of this possibility.
Okay, thanks.
Mm-hmm.
Hey, great work. I found it very interesting. One question that I had, and so I'm not an expert, so this might not be a well-formed question, but my impression is that MILP solvers have different solvers are good at particular things, and the encoding for a particular solver is kind of important to make sure it actually scales to problems. And that seems actually a really good use case for your compiler, right? That your compiler could be tailored to a specific solver.
Okay.
So if you have this type of constraint for this solver, you could compile it differently. Did you encounter this, or is that something you guys thought about?
So we didn't explore a ton of solvers, but we did explore two, the Coinor CBC and Gurobi. CBC is much easier to use in general, but it is very slow as compared to Gurobi. Gurobi is extremely fast. And so eventually we kind of hit a wall in our exploration, and it's well, as we make enormous problems, suddenly CBC starts to slow down. It turns out in practice, the APIs for these, it's all in C, so we just call directly to the C API. And the APIs are surprisingly similar. I mean, they both take a sort of compacted matrix format, and you throw it one constraint at a time, that sort of thing. And the actual interior representation, Gurobi has some more features, but we didn't explore as many of those, so we didn't take advantage of its outside corners.
I see. Great, thank you.
More questions? Okay, thank you very much again.
Thank you.